Hey everyone, my name is Trent Kelly, and this is my project for D212 data mining to clustering. And let's restart everything and shoot back up here. So the scenario is you've been asked to use clustering techniques to analyze patient data to identify groups of patients with similar characteristics, ultimately enabling better business and strategic decisions. This is the table of contents, so we're going to describe the purpose of our data mining, explain the reason for chosen clustering technique, perform data preparation, perform data analysis, and report on the results, and data summary and implications. So the research question, so what are the clustering patterns with the patient's age and income? I will be using the KMeans algorithm to determine the clustering centered around two numerical variables, age and income, and this will give the hospital some patient insight on the clustering of these variables. And my goal is to determine the clustering patterns with patient's age and income, and explain how the clustering technique you chose analyzes the selected data set. Basically with the KMeans algorithm, it's iterative. So just meaning it's going to cycle. And so it's going to have these initial centroids. It's going to assign data points to these clusters and update clusters as it's further iterates itself and just repeating. And then there will be a stopping point. And so with the initialization and the centroids, so you start out by telling the model how many clusters you want to start with. So it can be K1, 2, 3, whatever you choose arbitrarily. And then from there, assigning clusters to data points. So after the initial centroids are assigned, the model will perform calculations and start assigning clusters to data points. And it's going to do this by calculating distances between data points and the centroids, and then it's going to start placing them in their respective clusters based on distance. Typically, the distance is going to be Euclidean distance. And then it's going to start updating the centroids. And so with the initial cluster assignment, it's going to be random, but as the algorithm runs, it will start updating the model with new cluster values. And so the updated cluster centroid is based on the mean value of all data points with that specific cluster. And so the decision needs to be made: when is the algorithm going to be stopped? And what we did specifically for this project is I specified the amount of iterations that the algorithm will run, but you can set other stopping parameters, such as if the clusters are remaining unchanged, or setting minimum distances. And my expected outcome is to create a model that identifies the number of K-means clusters through an inertia plot and silhouette score. Now, this number is typically between 2 and 4 clusters. Summarize one assumption of clustering technique. And so the algorithm is going to largely be based on distance, and it doesn't account for clusters with different sizes or densities, and assumes the features within a cluster have equal variance. So this is why it's very important to standardize the data. It decreases that amount of variance and helps provide a more accurate model. Here's the packages that I'm using. And I describe one data preprocessing goal. So as mentioned above, standardization of the data is incredibly important to decrease that amount of variation present. So again, we get a good accurate model, or as accurate of a model as we can make. Identify the initial data sets with the variables. So I'm using age and income, both are continuous variables. Explain each steps. You prepare the data. So the data set is really clean for what I'm analyzing with age and income. There are no null values. Everything appears to be in order, so I really didn't do anything as far as cleaning the data. We'll provide a copy of the data set, library importation, and the CSV imports. looking at nulls, and without doing anything, there are none. With the info, it gives us, again, null counts and data types, and specifically what our columns are. I did change this, the naming convention of that. So the describe feature gives us like the mean, standard deviation, minimum, maximum, and overall counts with nulls. And the cleaning phase, so renaming and forward fill, you didn't need to do any forward filling because there were no null values. But this was old code that I used with previous assignments. And so it's creating my df filled rename, and it was just easier just to keep it in here because it doesn't change anything how it is. And changing the soft drink to no. This is based on the forward fill with previous data set. Changing an overweight value of the 0.709 to 1, and then decreasing the data frame down to 2 variables, age and income, and then printing the data frame. With the analysis, determine the optimal number of clusters in the data set and describe the method used. So the method that's used is the elbow method. I will look at the silhouette coefficient as well to evaluate the optimal, or evaluate the 3 clusters, and provide the code. This is what we're going over. So here's the reduced data frame with just age and income, the shape. So we have 10,000 rows, 2 columns, the means of age and income, pre-processing. So this is standardizing the data, and we are left with 2 columns and the mean of the new data frame. Here's a copy of the data set. And all right, so here is something that got sent back for revision, and I'm glad it did because it really helped me understand that I was thinking about this entirely wrong. And hopefully my additional learning and digging, hopefully I now have a better appreciation for what K-means and clustering is all about. So this is the inertia score, and originally, so when we're running this loop, I was thinking about it that it would show me, 1 to 15, just so I could see and get a larger picture on an elbow, which it does. However, the silhouettes or inertia score was running off of the last iteration of that loop. So it's looping through and going out to 15 clusters, and the original score I was getting, I was using off of 15 clusters. So I've reduced that down to 3. So because of indexing, that's actually 3, and then printing out this new score. So the new score is 7,469, which is not great. We want that to be as low as possible. And so our silhouette score for the 3 clusters, because previously I ran a loop to see what it would be on with different clusters. So I drilled it down specifically to 3 clusters only, and we have a score of 0.42. We want the score to ideally be as close to 1 as we can. The closer we get to 0, that indicates that we have loosely compacted clusters. The closer we get to 1, the more tightly compacted our clusters are. And if we are at negative, then that indicates that we may have misassignment of data, and the clusters may be inaccurately labeling data and inaccurately putting them in the wrong clusters. And so to get some actionable insight on what these clusters mean, how can we use them? And I did struggle with this with the previous submission, I was like, okay, great. I have all these clusters. I have silhouette scores. What exactly do I do with them? And I was thinking about it completely incorrectly. And so we have our inertia score and our silhouette score. And so what can we do with that? And so we have 3 clusters that are loosely compacted and are not great as far as labeling. So they are loosely labeled. So when we look at that and we look at the metrics from these clusters, this is what we get with the 3 clusters. And I have the describe function because I did some calculations to get what this information means. Because if I'm presenting this and I say, well, this, our age with the cluster is 0.88 to a person in the company, they may see that and not know what to do with it. So I've calculated out to something that is interpretable to others if I were to present this data in a business setting. And so what I've done is I've taken the standardized age, multiplied it by the standard deviation of the original whole data set, and then add the mean of the original age. And so I've done that with all 3 clusters. And so that gives us some metrics. This gives us some actionable metrics that we can look at if we're trying to analyze our patient base. And I printed out the minimum and maximum just so I had it on here so I could get kind of a larger scope on what the data consists of to see if our clusters are giving us a good overview evenly of our data. So this was sent back for the revision. So explain the quality of the clusters created. So when evaluating the quality of clusters, several things need to be considered. The iterative approach taken with the calculations requires a stopping point, which we've done through the iteration function. And I set a reasonably high number of 50, so that will have the algorithm run 50 times, and it will select the best number based on those iterations. And so the inertia measures cluster quality. Lower is better, as inertia measures how spread out the clusters are. DataCamp advises to choose an elbow in the inertia plot where inertia begins to decrease more slowly. And a good clustering has tight clusters or low inertia. Our inertia was close to 7,500, which is not ideal. And then the other thing that we looked at was the silhouette score of our 3 clusters. And so we have 0.42, so that may indicate that we have some accuracy. It's not exactly 0, but I would want to see that closer to 1. That would indicate that everything is fitting nicely, within that cluster. And discuss the results and implications of clustering analysis. This was also sent back for revision. So we determined that the 3 clusters brought about 3 distinct demographics on our patients. And so with cluster 1, from the calculations that we did from the standardized data, so we're looking at cluster 1, we have an age of about 39 and an income of 7,196. Cluster 2, we have an age of about 49 and an income of 35,000. And cluster 3, we have an age of 71 with an average income of 22,000. That's great. So that's what our clusters are or have identified as far as commonalities within the data. However, when we looked at the minimum and maximum, we have a minimum age of 18, a maximum of 89, a minimum of 154, and a maximum of 207,000. I don't feel that is accurately represented within our clusters. We don't have any cluster that is going anything close to $200,000, that being the highest one. In our age, we have a minimum of 18 and we don't have anything remotely close to that. The lowest we have is 38. And so I feel overall our model, and it makes sense with our clustering or our inertia score, sorry. The clusters are very loosely compacted, and with our silhouette score indicating that the data is not fitting tightly within that cluster, this makes sense, and this is what I would expect from the inertia and silhouette score. So limitations of data analysis. So the local optima is kind of an limitation of this algorithm. And the example I provided with the previous submission is if you're like climbing a mountain, you climb one mountain and there's a larger mountain that's covered in clouds. You can't see it, but you've climbed this really tall mountain, and you say, I've climbed the tallest mountain in this region, but you can't see this larger mountain that's covered by clouds. And so what the algorithm can do is it can get kind of stuck on large data points, and it won't recognize or appreciate the global scale of the data set. So what do we do with all of this? So yes, we have some metrics, and we have some clustering of types of patients that we would see in our hospital. However, based on the scores, I would say this model is not accurate, and it is not evenly showing the data, or fairly showing what we have in our data. So I would recommend that the model is to not be trusted. We have a low silhouette and a high inertia score. Further, when we analyze the model's cluster results and the minimum maximum of the original data, it just does not appear that it's capturing the depth of the data. We're missing a large variety of potential patients. So my suggestion would be to rerun the model with different variables to gain better patient insights, or to attempt to use an alternative number of clusters for analysis. But based on what we've seen, it's very slim that if we run it with any other cluster, that we will get markedly improved results. So I would consider using different variables entirely to see if we can gain better insight into our patients. So that concludes my presentation. Thank you for your time, and I hope you have a good day.